So back to today's topic, which is wireless sensors. Okay, actually, we also have the wireless sensor exercise, which is again a little bit heavy. A little bit heavy, but let me go through first the kind of the theory stuff, and then we go into the exercise part. So anyway, so today we are taking the wire in between the black box and, well, I have written there the cloud, but actually it could be any gateway or PC or whatever. So I'm not going to cloud today. We are just making looking at the technologies to connect the or cut the wires between the black box and PC. And also a little bit also about the power. So when we are going to wireless, usually it means that we don't even have the power, AC power available, since I don't see any reason going wireless if we do have the AC power. There are these modems actually that you plug just on the AC network, and which works as a data link, and those are something like €10 each. So very cheap equipment for that one. But wireless, going wireless always needs some requires a need for mobility. Okay, which means that you need to also consider some power there. And I start with the power. So the AC adapter. Okay, AC adapter should be designed only to power up the or charge the batteries. That's the main principle. Otherwise, you don't get any real benefit of being wireless, other than, well, it's wireless. Okay, so but AC adapter is an easy fix. You just need to basically check the power requirements and the compatibility of your power source and your equipment, and that's it. It's just electronics, nothing really fancy about it. Another one, okay, the battery. When you take a battery, then you need to consider different kind of things, since different battery chemistries actually work differently in different different environments. And for example, the lithium polymer technology, what we are using in mobile platforms like your mobile phones, it does not work in sub-zero degree temperatures. It just dies. It freezes over, and it may actually even be irreversible things going on. Same thing, I wouldn't take this to sauna either. So no heat, no cold weather for lithium. Okay, there are different batteries, and basically when you're designing an equipment, mobile equipment, you always need to consider, is it really outside, self-attending or unattended device? Okay, that rules out the lithium polymer kind of, or that kind of lithium hydride kind of batteries. Then you need to go into more traditional nickel hydride batteries or something like that, especially in Finland. In Central Europe, I think the lithium is quite okay. Okay, then when you are running on a battery, you don't want to replace them often, meaning that whenever you are having a battery operated system, then you need to also go into low power design. That's a state of art itself, but basically it means that on those battery operated systems you cannot use any more linear power voltage regulators. You need to go the switch mode power supplies there. Switch mode regulation of the operating voltage. And then you also, when you are in switch mode, you will start having the electromagnetic compatibility issues. Okay, meaning a lot of work. Anyways, making this work, for fun, for a while, it's not a big deal. Okay, the operating voltage, of course. Okay, this far we have been using just this mini proc to power up these devices, but actually that 3.3 volt power supply is probably nowadays the most common voltage to operate any system. 3.3 or lower, but usually it starts from 3.3. For example, today's exercise, we have a okay, this kind of nice small module of 2.4 gigahertz data transceiver from Nordic Semiconductors, very popular on the hobbyist. It's also is okay for commercial use, but this is the very simple to operate radio modem that it's pretty fast, actually fast enough for our applications, especially the sensor applications. But okay, 3.3 volts, the operating power. What makes it actually good on this kind of educational environment, that we can actually have 5 volt data lines. Okay, so since well, this prototyping set, this development kit, what we have has the LCD. Unfortunately, the LCD is designed for 5 volts. So having 5 volts LCD, you need to also have the CPU running at 5 volts, but then interfacing with a 3.3 volt module, you just need a there. In this case, you need only to take care of the power of that module, and the data lines can be still 5 volts. That is not the case on most of the cases. Usually 3.3 cannot tolerate, even on the data inputs and outputs, it cannot tolerate 5 volt signals. But this is a exception. All right, some wireless communication technologies. First that comes into mind is, of course, the Wi-Fi, meaning the what is it, 802.11g or whatever the standard is for the wireless internet. Good thing about this Wi-Fi is that it's standardized, excellent bandwidth, direct connection to internet. Okay. The bad points: expensive. Those modules are quite expensive. Bulky. But the worst part is very high power consumption, easily watts when it's active. Watts compared to some of these other technologies here, which are milliwatts. And also the Wi-Fi, it more or less requires that the node is always on to maintain the same IP, which would make it easier to handle. Anyways, this also the pros maybe. Well, it's already there. Direct connection to internet, meaning that if you have a sensor on with a Wi-Fi connection, then it can directly upload the data to the cloud without any gateway. Okay. But anyways, I would rule this Wi-Fi out just because of the very high power consumption. Unless, of course, if you are running a Raspberry Pi with a lots of battery power, then it already have the Wi-Fi there. Well, and the Raspberry Pi actually consumes already few watts when it's on. Okay, what is 1 watt in addition to that? Nothing. All right, the next one, Bluetooth Low Energy. Okay. Bluetooth Low Energy has most of the, well, it has mostly just the good things about it. Pros, yeah, standardized, strong standard. And yes, very low power. It's simple-ish. Lots of examples available, of course. Robust, and it's compatible with the well, your other handheld mobile devices. Okay, cons. Well, the low energy of Bluetooth, Bluetooth low energy part is based on that it's not on all the time, but it just wakes up and sends data or receives data and then goes back to sleep, which is not good for streaming. If you need big volumes of data, then this is not anymore low power. Then it's just Bluetooth without no low energy. But it's capable of doing both. So, but anyways. Then we have this 2.4 gigahertz RF. I just mark it like that since that is internationally agreed that there is a free band right there for anyone to exploit. And there are, for example, this device, what we will be using, 2.4 gigahertz radio transmitter or transceiver, transmitter receiver module that runs on this band. It's also license free, and the basically there are only two bad things about this technology. Well, one is the proprietary technology, meaning that if you are getting a module, you can never actually change it. so only the usually only this is manufacturer dependent devices, so this can only be connected to another one from the same manufacturer. So they have proprietary the radio transmitting scheme there. And of course, when you have plenty of these, then although this can be set into 512 different channels, if you have a lot of these, then you might actually end up having, the different devices on the exactly same channel with the same address. So, okay, so not necessarily a good idea. And also 2.4 gigahertz is the area where Wi-Fi is also there, Bluetooth is also there. There are also other radio frequencies around there. So basically you need to find a channel which is free. Yes?
What's the range approximately in meters?
About 30 meters. Basically, as long as you can see it, it's okay. Yes. I think this is something like up to minus 11 dBm power. So it's in milliwatt range. Okay. Then the last one there, Zigbee. I think that's also running at, was it 2.4 gigahertz range? But it's again a proprietary industry standard, yes. Widely used, yes. Low cost, yes. It has almost limitless number of nodes, but the power is about the same as this NRF device what we are using. The cons basically is that it has a limited data range, only up to 250 kilobits per second. And then there are some serious security issues because this is totally open without any ways of actually any add some security into it. So you can have a one device that just listens there and just waits for data to come. So unless of course you make your own, so basically secure your packages. Yeah, encrypted. Yes, of course you have always encrypted. Okay, but anyways, and then the Zigbee. I actually kind of played with those three different Bluetooth low energy, this 2.4 gigahertz and Zigbee. And the Zigbee actually, it's kind of funny since you, in order to make a network out of Zigbee, you need three different kind of operating mode devices there. Okay. You cannot, in Zigbee, you cannot make point-to-point unless you have one point in between. That's a kind of funny thing for a, it's limits usage quite a lot. This 2.4 is gigahertz, this on NRF24 is actually excellent for point-to-point. Which means it's then, well, if you can do point-to-point, then you can actually start building your own network if you wish. I don't recommend it though. But it also have the construction that you can have up to 6 devices that are connected to one single kind of router or access point device. Bluetooth low energy, a little bit too much of coding there. You need to do the device discoveries and that kind of stuff, which are not fun. It's just, you know, it's just coding. All right, so we'll stick on this one. Okay, when you are selecting the technology, of course, you need to take a look at the different or your what is your target there. If you really want a access directly to mobile devices, then it's the Bluetooth low energy, period. If you need a kind of network that automatically makes the connections, then it's Zigbee. Then you can have a mesh of sensors. Okay. This 2.4 gigahertz, what we will be using is just the simplicity of it, what makes it good. Okay. Wi-Fi, high bandwidth. So basically only high bandwidth technology on this wireless is the Wi-Fi. Okay. So we will be using on this, is it 4th lab or 5th lab? 4th lab. Nordic Semiconductor NRF24L01 Plus chip. And not just a chip, but a module, which something like about, is it less than 10 euro each? Low cost. It uses this license-free 2.4 gigahertz band, ultra low power, meaning that on standby mode it's microamps. On active, so basically sleep mode is microamps. In standby mode, meaning that it's listening transmissions to that address, then it's milliamps. And when it's sending, then it's also just tens of milliamps. Receiving is, well, the same milliamps. level, of course. It handles the packets automatically, so you just need to provide the address information and the package, the data payload basically. After some, configuring of the device, of course. And also automatic packet transaction handling, meaning the handshaking. Did the package actually go through or not? Then, as I said earlier, it can actually have also this kind of 6 data pipe multi-receiver, what they are the Nordic Semiconductor is calling this mode. So it's basically a one device that can be a transceiver for 6 other devices. Okay, low cost. Yeah, near range communication only. So within the vicinity of this device. I think Juho Vesanen checked how far you can actually reach this one. When you see it, it can be up to 100 meters, but if there's anything in between, then no way. So, and it actually on these steel concrete kind of buildings, it can go around one corner, not 2 corners. It's still, these 2.4 gigahertz, the waves, they are kind of bending on the sharp edges. Okay, and how to operate it? Well, it's register based, same as those SPI or those serial line the sensors what you used last week. So basically this has a SPI bus. I think it also have the I have seen a module with the I2C also, but SPI is the most common way of communicating with this. It's the rather fast way of communication. Okay, block diagram. Think I mark yes. So it has this RF transmitter and receiver. So there are these modulators, filters, and then the power amplifier, and then there's the antenna is connected to RF receiver amplifier with a gain controller, and then the filter, of course, and this demodulator. So the GFSK, that's stands for something frequency keying. G is for I don't remember anymore. Well, anyways, it's kind of the transmission scheme that this one uses. What it also requires, this is a chip, and it requires the clock crystal there to generate a 2.4 gigahertz signal. Then of course power management. Then there's the baseband. There's a transmission FIFO. So basically there is a 32 byte transmission buffer. You can just write the payload there directly, and then when you just ask the system to send it, it starts transmission. And then there's some sort of enhanced shock burst baseband engine. Okay, and receive again 32 byte payload FIFO there. And some radio control, meaning that okay, we have that 500 some channels you have to select. In order to do any transmission, you have the transmitter and receiver on the same channel. Quite, nothing magic about that one. But anyways, that part is the magic part. We don't need to actually care of what happens inside of the system, as long as we actually connect the device on a SPI bus. Use SPI to connect it to the microcontroller. There are also a couple of extra signals also there. Okay, this device can be set to give interrupt, for example, when we have data payload ready. That's nice. You don't need to poll all the time. Is there something coming or not? It can just give the interrupt whenever there's something ready. Okay. Chip enable. Okay. There's the SPI chip enable is here. So basically, that is for data transmission only. This chip enable means that basically it's a power switch, on or off. So if you set the chip enable inactive, then basically this goes to sleep mode. No, it's power down, so it's a deep sleep. It doesn't wake up. On the chip enable on, then it basically automatically start as a receiver. Okay. Yeah. Hey, wait a minute. Green. Ah, yes, the green circle there. Register map. Okay, so we need to set up some parameters to the registers. For example, the what channel it uses, and also what address it actually uses, and what is the addressing mode. All right, so data control interface for that one. VCC is the power plus 3.3 volts. Do not use 5 volts, otherwise you need another one of these. Well, and then the ISP bus, SPI bus, SPI bus. So basically they have those 4 SPI signals and then interrupt, and it can be actually controlled by 3 different interrupt sources. Okay. So chip enable is actually to activate the chip in receive or transmit mode. SPI command, similar to the any SPI device. So basically all the SPI transactions start either if it's a read or write operation, it always starts with the command word, or actually command byte. 1 byte starting from most significant bit and then ended to least significant bit. So yeah, that's the one of those modes of the SPI. I think it's mode 0 and 1, right? And then followed by the data bytes, and here, okay, first goes the least significant byte, so that it starts from the most significant bit, and then the next byte, and so on. So bit order is the most significant bit first, and then the byte word is the least significant byte first. Okay. More information about the details of those commands are on the datasheet. So basically this is example how you read receive data. So now we have somehow first got the information that there is data has been received, for example by that interrupt. So first the activate the SPI interface, then reading the payload register by having the command hex 60. So that will be the command byte hex 60 followed by 1 dummy byte. and that dummy byte is basically for the dummy byte is so that basically the first let's see, what is the read operation? Yes, so the first byte doesn't actually matter, so the next byte will be the first byte is a status and second one is, oh okay, what is a dummy byte? Yeah, when you are writing, yes, of course, yes. So you write, remember the SPI, you only write to the system, and then it's also receiving the data at the same time as it's writing. Okay. So when you are sending this receive payload with command, so 0x60, then during that operation you get the status register, and then basically you write a dummy byte, and after that on the SPI buffer you would have the width, so width as the received data on your SPI. Okay, now it makes sense. Then you basically start new transmission by putting the CSN inactive and then active again. Then read the the receive payload, receive buffer payload by that command 0x61, followed by how many bytes did you have there. So basically the width of the receiver buffer amount of dummy bytes, and each one of those individual SPI transmissions you need to basically, when you send it, you wait until the transmission is done, then you go and read that data and put it somewhere safe. Okay, and the same way, whatever the command is there, actually when you are setting the command, the device always gives you the status of the chip, and at the end of transmission by setting the CSN inactive. Okay, that's all. Let's take a look at what happened. All right, there. So today's exercise is about making this kind of system. Let's see, I have the 1, 2, 3, 4, and I will give you these transceivers, and yeah, so here you are with some wires and 3.3 volt regulator. So that 3-pin device here is a 3.3 volt regulator that you need to use to power up the device. All right, so we will have first a sensor here, and to make it a little bit easier, I think I've selected, yeah. Yes, there's the one wire temperature sensor. So after doing the first exercise, or the third exercise, you should be able to just repeat that part on the on that 1820 at the 1820 one wire temperature sensor. So to get some values you can send. Okay, then there's PSOC connected to LCD. Then you have the NRF module there with 3.3 volt power. Remember that one. Then I was a little bit optimistic about the multiceiver that I would be doing, but unfortunately I had a little bit too many things to do this week. So basically someone could take and instead of doing this part, do the multiceiver part. It's basically it doesn't add much of the complexity. It's as complex as the transmitter. Okay, I just need someone to start on that one. And you will be starting this project. I made actually some things. Let's download that one. Downloading it there. And then I could actually extract all, not downloads. Just extract that one to piece of projects. Make a new folder there. Did it go okay? E4. Okay, yeah. When you open that design, actually you could just clone the project, or you can actually start it directly from there. I don't care. I don't care. You can either clone it or just start using it. What I already did, I did some pre-design. Otherwise this would have been a little bit too heavy in my opinion. So I already have defined their NRF24 SPI module and connected it into some ports. So the input port for SPI, so MISO port is port 1.0 and MOSI port is let's see, port 1.2. It looks like, oh no, 1.1. Then the clock port is 1.2. Then the chip enable. Okay, this is the not the SPI enable, but the chip enable is port 1.4, and then there is CSN is 1.3. So that SPI enable signal is 1.3. Those are already predefined modules. Okay. Main is empty. But okay, this is the hard work. What I saved you a few hours of typing, or actually a couple of hours typing just this. So I have predefined names for these the mnemonics of that chip. So for example, the read register mask and write register mask, meaning which bit is actually the you can mask the the command, for example, use that one to mask with the command. Is it read or write command? Then the commands following. So there's, for example, the read payload register hex 61, or write transmit payload is 0xa0, and so on. So those are the commands. Configuration, okay. So registers and the register masking bits are following. So basically, configure register is register 0. Then there's this the bit masks. So for example, to okay, those are basically the same mnemonics as in more or less the same mnemonics as in the datasheet you can find, and so on. So these are bit masks for each of those register contents. What is the basically in configuration register the CRC bit. Same, for example, here the enable auto acknowledgement data pipe with, okay, this actually is about how to enable a data pipe on this chip. So single node transceiver needs only one data pipe. It can actually have several, but it makes it a little bit cumbersome to use. So in our case, we are using this kind of configuration. Multiceiver, node 1, node 2, node 3, and basically you have the data pipes only between this these. So one is actually kind of data collector. So basically on most of these devices you need only enable one of those data pipes, which is the well, usually this the lowest data pipe. Okay. Receive address. Okay, this is basically turn the pipe on. What else? Set up AWS setup address. Which and for all pipes. Okay, yeah, and so on and so on and so on. So basically, although I have written all of these definitions there, you still need to take the datasheet of that thing and start really reading until you find the correct points. Oh, FIFO status, okay, transmit address. But anyways, I also have couple of routines already written there to help a little bit of the communicating with that device. By the way, I have just tested that it gives the status when you start communicating. I have just tested that the communication works, nothing else. So first, just starting the whole thing, the first function is just to start the those modules, and it returns the status register. As you can see down here, there's a So these are just starting up the modules of the required for the communication. Then the command, okay, it doesn't need to be the array, but anyways, it could be only one byte there. But anyways, I use 32-byte registers there, or the variables just for fun. And basically, the first variable now is the no operation. So basically, by setting the NOP operator command to NRF chip, what it returns, it should return just the status, nothing else. And then I made this command on NRF24 command function that actually should do the data transaction with the device. Should do. And it did for this NOP operation. And returns always the status. Okay. This is the most used subroutine to communication, since you just need to let's take a quick look. My slideshow, where is it? Okay, so each SPI transaction starts with the command word followed by the data bytes. If it's reading, then the outgoing data MOSI data payload is just dummy bytes. If it's a write operation, then the read is usually dummy bytes, except the first byte is the status. But this function actually helps. Whoa, what happened? Oh, I lost the picture for a while. So this subroutine actually helps you communicating with the device. So it first goes and sets the makes sure that chip enable is on. Okay, this is it could be on a power down mode. If it's power down mode, then you don't even need to write anything there, since it's really power down mode. So chip enable, that the not SPI enable, but chip enable must be active. Then basically you start the SPI transmission, and then you just do the command transmission, and for each so byte by byte, so that one actually sends the data, and then this one just waits that the SPI transaction is done over, and then basically on the read buffer of that or input buffer of that SPI module, you should have the incoming message. So you just do byte by byte transactions like that, and after that, well, end of transmission. And okay, this function actually returns the status register just for fun. No other reason, just for fun. Okay, so those are the tools. So the rest of the task, well, clone the project or just start working on it. You might actually change the name at some point. But anyways, the data comes from a simple the one wire temperature sensor. And just repeat what you did on the third exercise. Then what the system should do is to read the sensor data. Okay. At sampling rate of about 1 Hertz. Okay, it seems that I've been copy pasting here a little bit. And then basically test that you have this part working. So it should compile, but well, and they are already the subroutines for the SPI or the NRF system, but check first that you can read the data from your one-wired sensor before continuing. All right, then powering up. First, add there that 3.3 volts voltage regulator and observe the pins. Oh, okay. I have the data sheet here. Okay, it's very simple to add. And actually, we are now in a so small the currents that I don't think that these capacitors are really required. It's only one device which already have also some bypass capacitors. Well, I will get you some capacitors just in case. So that's the connection. Input and ground, so you put the 5 volts in and then you have ground connection and the output is that 3.3 volts. Very simple. And here, okay, that's the package. So ground is the leftmost, center is out, and in plus 5 volts in on the other edge. If you basically reverse the polarity, you will have a short. Nothing bad happens other than basically you are just actually loading your USB bus a little bit too much. Okay. But anyways, observe the pin out. But this is very simple way of making a 3.3 volt power for that chip. Okay. What else? And then basically just add the transceiver into your design. Oh, there's a couple of pictures. Okay. Pin out. Pin out. So those are the pins. And as you can see, that's actually from the top. Is it the top view? Yeah, it's a top view. And actually, I think it's... all right, excellent. So this module actually even have the those prints there. Your devices don't have it, right? Okay, good. So it was really good that I actually marked those. My device actually have the pin out marked on the seal screen. Okay, so match the pins. So blue ones are the signaling, normal signaling. The IRQ is the interrupt signal from the device. Then that VCC here is 3.3 volts, ground 0. Okay. And here make sure that this module is powered to 3.3 volts. As I said, these signal pins are actually they are TTL level compliant, so actually they can handle up to 5 volts, but the power not. It'll burn something if you turn 5 volts there. Okay, and this basically defines the pin out what you should be doing on your design. Okay, you can also, let's see, yeah, so there's the interrupt. NRF24 IRQ, which I haven't defined on the design. So you need to actually select some of those pins as, no, I have done it, sorry. So this pin here, NRF24 IRQ, is defined as the standard, well, the drive is high Z, but it's falling edge, it gives falling edge interrupt. You just need to activate it. How to activate it? Library files, library source files. This is an I/O pin which is just renamed, so basically we should find the GPIO interrupt routine on this section, and basically you need to put the hook up to your own code there. So when you enable the global interrupts, you also need to enable the GPIO interrupts. Then after that, this will be called when there is an interrupt from the this radio chip. And basically you should put here your custom code. I will just write it here, something just for fun. I comment it just for fun. So if you actually put here long call to your own routine, for example, your own routine would be NRF24 interrupt service routine. Then basically you just have to make the corresponding, for example here, interrupt service routine for RF link, and type void NRF24 ISR. And if you do it like this, then basically after the GPIO interrupts, it goes there. Okay, but returns also back here. Okay, it's just an ordinary call to that routine. There's also another way of actually making this interrupt to work. You define your NRF24 ISR as the type of interrupt service routine, meaning that the compiler then uses return from interrupt at the end instead of ordinary return from function. So there are two ways of actually doing the interrupt services. You save few cycles if you do the define this part as interrupt service routine. Now it's a normal function. Okay, I will show you also the other one so that they don't mess up each other. Interrupt service routine as interrupt service routine void. Same thing here, 24. Let's me put it like this. And if you say pragma, how does it go? Pragma something. Oh, I need to take a look. Pragma interrupt service code. Right, application note. Interrupt handler, yes, that was it. Now, this routine would return directly to the interrupt point. It doesn't come back anymore to here. So instead of long call, I could actually have just long jump to NRF 24 in ISR2. Okay. So that's the way, actually, the first way, which is now the number 2. This one basically goes to that NRF24 for ISR2 routine and never come back, but basically return directly from interrupt from that function. The second one, which is the original one, this is kind of just ordinary function call. Okay. All right. So and this is would return, except the previous line actually jumps there. So those two different ways for the interrupt handling. You need only one. It's up to you which one you find better. Earlier we did, or you did the hookup on that A to D converter. Then basically on that case, since there were already also some code on that other code after that point, where we added the hookup, there was also something else here. So when there was the A to D converter was ready, conversion was ready, then you could do the hookup to your own code. There you couldn't use long jumps, since otherwise the rest of that code on that subroutine wouldn't have been done. So that's why there's just a normal function call. Okay, complex, right? A bit, at least for me. Okay, so that's the way to basically have a link to your own code on your own interrupt handler. My recommendation on this kind of code is that you, I think I have said it before, but I say it again. When you have a interrupt service, you want to have as little as possible done in that service. So basically just set a flag. For example, here you could just set a flag when it has this interrupt comes. It sets a flag. Now there's something, there's data ready on the device, and then on the main loop, on the main while forever loop, you would have the handler for that task. On a real operating system, you would actually have this interrupt service routine that gives a request for a service. That would be the hookup to your the low-level assembly code interrupt. It just sets the request to handle it and saves only the data which is required on that handling. Okay. And yeah, then there's that fundamental pre-written software empty main file. Then there's the header file with lots of predefined stuff. You can use them or just, you know, hardwire these values. Fundamental functions. I have that byte. The first one is to start the required modules. The another one is, I think there I have wrong name. Let's see. Yes. Sorry about that. Another one is actually an nrf24 command that basically writes the command and reads or writes the payload to or from the module. All right, when you have that done, basically this is what you should get. The first test, if you first call on this nrf24 start, it should return 0x0e, which is the status register after reset. If you get something else, if you get, say, values like hexadecimal 00 or hexadecimal FF or hexadecimal AA, A5, 5A or 55, that's probably because the data, you don't have a connection to your device yet. But it should give you the 0E. Check that one. If it doesn't work, back to the salt mines. All right, then some functionalities. So this is just to make sure that the can communicate with this module. All of that stuff. Then you need to write some functionalities. Who would be doing the multisiever? Any volunteers to do the this part? JP? You could try. Excellent. JP. Okay, so first use the channel 5. Why I picked 5? No reason. So it sounded so good, you know, channel 5, yeah. Is it channel 5? Wait a minute, that is some sort of the channel 5, that's a some of those perfumes, right? Okay, that's why I picked that. Yeah, I've been watching too much TV. You know, those commercials, they started on 70s to have channel 5 commercials. All right. Okay. and then you need some addresses. Okay, pipe numbers, which basically, well, I just picked a kind of easy way to say having the addresses. So they basically just pipe number is changing, and otherwise hexadecimal A B C D E F 18. 18 is the 2018. It comes from that one, and then you have the pipe number. Okay, pipe number 5-byte operation. Your pipe number or the device address is actually 0, 0. One, 2, 3. Got it. 3, 2, 1. Okay, good. We would be use so-called enhanced shock burst operation with the CRC enabled. It's always enabled, and then encoding scheme. Wait a minute. Yeah. Okay. Wait a minute. There's something funny on that one. It's 1 bit. Well, anyways, it's one. I think it's byte. Well, need to check it. Okay. Then you also enable the automatic retransmit. You can either disable or set it so that it can go up to 15 retransmits before giving up. Good idea if you have several devices on the same place to have actually that retransmit, since you are communicating on the same channel. And yeah, there is a reasonable chance that you will be communicating at the same time, meaning that then it doesn't go through. Okay, air data rate, we are using the lowest data rate, 250 kilobits per second operation. And this is for, well, basically for all. Enable receive data ready interrupt only. Unless you want to get fancy and also put the transmitter well, when the transmission is over, also as interrupt. But then if you do that one, if you have only one interrupt source, it's much easier to then handle basically what was the cause of that interrupt. Okay. But it's up to you. You can, since there's only one interrupt line, then you just need to, on that interrupt service routine, you just need to check what was the reason for the interrupt, and then just have the flag going up for that single, or it could be actually both, or more than one reason what to do next, basically. Okay. And what it does. Nodes 1, 2, 3 transmit the current temperature reading. Okay. As ASCII coded string. So you have done already ASCII coding of that on exercise 3, showing the decrease in Celsius on LCD, basically just sending that one to the pipe once a second. So just have a sleep timer loop, for example, and just once a second go read this one wire, the sensor, and then just transmit the string the data pipe. And of course JP will be receiving those and showing them on the LCD. Okay, let's see. You would be also sending something once a second, just any string once a second to all of those data pipes. So then you can basically check well, both transmission and receiving of any of the devices. Yes, this will be so much fun. Good. All right, and there's what would the for these nodes 1, 2, 3 interrupts when data is received, saves data and prints the data on main loop. So basically, interrupt service as short as possible, just having basically a flag that then go and read the whatever the receive buffer is, and then print out whatever there is. It should be a string. Okay. Yeah. Okay. Okay. There are some instructions how to actually do the coding there. Just hints, but what I would like to see is your temperatures, all of your temperatures in your device, and then a string sent to your devices, and you will show that string into your nodes. Hmm?
I'm a bit confused. The receive data, that means the string he's sending and not the data from the sender.
Data. Well, it's a data payload. It's a string.
So that would be what you
Yeah, yeah. It's a string. You know it. It's already a string, so it helps on handling.
like if data is meant the data from the sensor or the data the module receives.
Huh?
I had my confusion was that there are two data.
Yeah. Okay, yep. Yeah. Yes. Yes. So temperature data sent as a string, and then that string sent as a data. Yes. Okay. Did I confuse you more? Okay. Then let's, before going further, okay, this is your main source of everything. Okay, did it download it? Yes, PDF file. This gives you all the information what you need in order to communicate with the device. I have provided that simplest possible communication interface code, and I have tested so that it gives status. There might be still something wrong with it, so no guarantees. If there is wrong, fix it. It's called engineering. And how does it go? Whatever comes for free. Okay. All right. So basically, there are these electrical specifications you don't need to worry about, other than connecting the right kind of voltage as a power. Remember 3.3 volts. Everything else is already taken care on this module, including the antenna. That's nice. Including the antenna. So we can skip basically those two. Then, okay, operating modes. State diagram. That shows what happens when you power it up. If the operating voltage is less than 1.9 volts, then basically it's kind of in reset undefined mode, but then power on reset happens at 1.9 milliseconds, 1.5 volts. When it does the power on reset automatically and goes to power down mode. When you basically set the power up mode, then it goes and starts the crystal oscillator and goes to standby 1. Okay, so standby 1 is the mode then when you can start actually receiving data, or you can also start configuring. In power down, you cannot do much more than just to power it up. Well, that's power up is the chip enable. Okay, and so basically you will be working mostly on the standby 1 and standby 2. So basically, depending on which register values you write there, it's either on receive mode or transmit mode. Okay, so basically it's either transmit or receive. So immediately when the transmission is over, it goes automatically into receive mode. Nice. Hmm? Where? Okay, yeah. The receiver actually sets in 130 microseconds, so it's not immediately on when you are going from the standby mode. Okay. And then some yada 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 blah blah blah. Okay, and standby 1 and standby 2 were setting. Okay, this power setting the power up bit on configuration register. The device enters standby 1 mode. Yes. Yeah, standby 2 mode is extra clock buffers. Okay, yeah, so basically it's standby 2 is ready to send as soon as you upload there something, and so on. Okay, and these are the registers settings. Okay, for receive mode you must have the power up bit high and this register high, and of course chip enabled. Transmit mode, basically you just set this receive bit to 0 and then it's ready to transmit. Okay, and so on. Timing, yeah, it needs some timing in between of jumping on from one mode to another, which you should take into account somehow. Air data rates, we are using the 250 kilobits per second since that's the most robust data transmission. When you're going higher data rates, of course, then there's more room for error. Okay, so yes, lower air data rate gives better receiver sensitivity, but high air data rate actually the average current consumption goes down, sending the same stuff in less of the time with the same power. Okay, this is also compatibility. Okay, they basically made the first version was without that plus, and it has some issues. Then they fixed the issues for that plus version, plus made some couple of additions. The RF channel, okay, the base channel is 2500 megahertz, and then setting up the channel number, it just gives you the how many megahertz from that one. So channel 5 is at 2405 megahertz. Okay. There is also received power detector. that helps basically on finding if there are any channels. So if you are not, you can make a system that listens, from channel to channel, and try to find if there's anything there. Kind of auto setting the channel or reverse engineering data. Okay. Some other stuff, and there's also the power settings. Okay. So basically, the highest power is 0 dBm, so it's 1 milliwatt maximum power, and then minus 18 dBm is something like 1/8 of the watt. No, 1/16 of watt. Uh, 6 dBm is power is going down by factor of 2. Right. Oh, well, whatever. But anyways, yeah, I don't see any reason why to save power in this exercise. Okay, then there's something about this enhanced shock burst. We are using that mode, and basically we are using this 6 data pipe multi-receiver network. Well, just only 3 active ones. But anyways, there's not much to read in here. Just configure it correctly so it uses that mode. And this is something that the system does it for you. Okay, and now I see that I have a typo in my typo here, not bit but byte. That's the magic what happens inside of that chip. You give it a payload, give it the also somewhere the address, then basically this chip puts the preamble, basically that's the start of transmission signal, so that the receiver knows when to start listening, and it's followed by the address. So basically now the receiver can start watching for the specific address for that chip, and then there's a packet control field which is also automatically generated by this chip. Payload is your payload. Cyclic redundance check is actually also calculated inside of the chip for you. All right. Excellent. They are using the best ever preambles. 01010101. Why? This is the way you can actually synchronize this channel, since there's always a little bit of drift of the data transmitter receiver. You need to fix the this or synchronize it. It's one point, and that's the perfect bit combination to actually use. USB also uses that kind of preambles. Okay, payload length and package interval, and so on. And this is how you calculate cyclic redundance checks. Okay, great. Automatic packet assembly is there. Okay, this is automatic. It's done for you. Okay. Automatic packet disassembly. Okay, so basically what you just need to do is to set the payload and say transmit after you have done the of course the configuration. Same way, when the automatic packet is disassembled, it appears as the data payload on the receive register, and then if you have the interrupt pin for receive data ready, then it interrupts and then it's ready to read. Okay, there is also the auto acknowledgement. Okay, we will be using that one to check basically that JP has done his deal. so, so basically to receive the data. You also need to basically take care of that one. So there's nothing happening here for the transmission. Then it means that you don't have the device getting any data yet. Okay, but that's also automatically done. Automatic retransmission. Well, it's automatic again as soon as you just set it up correctly. Yeah, and the there we go. And that's the flow chart. How does it go? And let's see. Oh, right. Here we have. So this is our the network configuration. PRX device is the JPs, and then we have a PTX 1, 2, 3 there. The devices, okay, and basically those LNA gain. Well, I've set the air data rate, but LNA gain I haven't tell you yet. Let's use the default for LNA gain. That looks like it. The common, it should be common for all, but well, anyways. Okay. Each pipe has its own address, so it's both receive and transmit address. On the device side, it's easy. You just set the receive and transmit address at the same, which is A B C D E F 18 and the number. Okay. This is an example, so basically based on this example you can start doing your own design. So receive and transmit address of PTX1 are the same, and it should actually then be same as the address data pipe 1 on the PRX. Okay, good. Then there are some timing diagrams. Good. More stuff, more timing, more timing, more timing, more timing. Oh, ooh. Stroke burst package data and control interface. Okay, now we are going to the actually the important stuff. So that's how you connect it. Okay, the SPI can be actually configured up to 10 megabits per second. That's the highest clock rate. So basically you need to divide the chip clock by 3 at least. Highest 10 megabits per second. And yes, there's the command word followed by the data bytes. That's the format. And these are the registers I already basically have given you some mnemonics on that header file. So read register, write register, command, and this basically AAA is then this the register number. So for example, writing to a register let's see. The registers are then okay, where the register map? There. Okay. So writing to a configuration register. You need to take that RX or write register command at the beginning and add the register number. So let's see. So this not actually address 0. Let's see what was the right register. So write a register. So the command actually comes from write register okay or 0x00. That would be, well, the same as that one. So write to register. That's the what was that? Configuration register. Config. Yep. That's a config register. Okay. Combine these. This is your command, followed by the byte. It's followed by this byte, and there you can actually set these different values bit by bit. So setting the prim RX to 1 would require setting the prim RX, and so on. So those bits are then set by, okay, let's see, does it make any sense now if I have my code mnemonics. Oops, not that one.
There's a small mistake on line 19.
Where?
On the reuse TX payload, there's a
Yeah, you're right, sorry. Yeah, that my mistake. Line 19 of my the RF24H. And of course it didn't have any syntax error there, so it just compiles. Okay, yeah.
It's not the
Yeah.
command you use often.
No,
Just
yeah.
one of the last payload.
So yeah, so okay, using the mnemonics. So that's where? Wait a minute. Config. Yeah, config mask. Configuration register. Then you can mask these bits. For example, you just add there. For example, the next byte would be the write to configuration register would be the on NRF. Oh, actually, well, that's power up, or let's see, CRC 0 or max RxDR. Okay. Okay. So that one sets the bit, which tells interrupt when the received data ready. Power up and whatever else bits you need to do to configure the device. So basically these 2 bytes would be on your command. Okay, command also. So that's the command 0, and this is the command 1, and basically then you just to do this command to the device, you just set the this my excellent code on RF24 and command with the command, and then some maybe status values somewhere and 2 bytes transmission, the length of that command. Right. Makes sense. Maybe. And this one actually returns status of the device. Got it? Not yet?
So the write register is what you have there as write register mask. Config then would be config this.
Yep. So configuration register is 0.
So there's not a thing you defined. Just with 0. I'm not sure if I understood if the config you use there is something which is defined in your kernel or just by a constant.
Ah, sorry. Yes, yes. Okay. I didn't remember how to use this one anymore. So, and. Okay, okay. Yeah, yeah. The way I actually define that one basically is the. Let's see. Let's see. I may have an error here. The good thing I didn't actually affect on the it gives the status all every time I actually write there something, so there might be an error that actually didn't come out in my test. Write register. Wait a minute. This, yeah, there's an error. Okay, let's work on this together. I'll just shut my streaming and recording, since this will take a little bit longer time.